Good morning, everyone. So today we will wind up our optical isomerism with the discussion of two molecules that are there in your syllabus, and that is lactic acid and tartaric acid. So I have discussed this previously in our live session, so it just would be a summary of what we have done in here. So let's discuss the first molecule that is there in your syllabus, and that is 2-hydroxypropanoic acid. So this is the structure of that compound. Okay, so if you number it, obviously carboxylic acid will get the first priority, so it would be 1, 2, and 3. Okay, and if you look at this molecule, there would be one chiral center that is present at the second carbon, because second carbon is attached to 4 different groupings. So since it has one chiral center, how many isomers are possible? 2 to the power of 1. So there are 2 stereoisomers possible in this case. So that is what I have drawn here, the 2 forms of tartaric acid. As I told you before, the carbon chain is usually kept on the vertical bond. So, and it's always kept that written in such a way that the first carbon, the first priority carbon, is coming on the top of this particular vertical bond, and then you arrange the substituents accordingly. So here I have drawn 2 different stereoisomers of this particular molecule, that is 2-hydroxypropanoic acid, which is nothing but your lactic acid. Now, as you know that these are not superimposable, so that means they are optically active. So if they are optically active, means they would be able to rotate the plane polarized light. So if they are rotating the plane polarized light to the right side, it would be a dextrorotatory. If they are rotating it to the left side, it would be a levorotatory. So in these molecules, when they studied it, they found that this particular configuration in which you have written this particular stereoisomer of the lactic acid is showing a levorotation. That is, this minus sign represents the levorotation. As I told you before in the starting class, this can also be represented by a letter called small l. However, this particular stereoisomer is having a dextrorotatory activity, which can also be represented by a letter called small d. So these things we have already discussed in our previous lectures. Now, here I have written down some other terminologies like capital L and capital D. So what do you mean by this capital D and capital L? This is nothing but when you write this Fisher projection in this manner, what happens? The penultimate stereo center, that is the one that is just prior to the ultimate carbon, okay, that stereo center, if you write it in a Fisher projection, if OH is coming on the right side, then we call it as a capital D, and if OH is coming on the left side, they are represented by a letter LD. These are way of kind of configuring the stereo centers, which we learn in advanced stereochemistry. But since this you will find in some textbooks, I'll just mention you what they mean. You don't have to worry about it. We will come across these terms when we study the biomolecules, where we talk about carbohydrates. Now coming to the second molecule that you have in your syllabus, and that is 2,3-dihydroxybutane dioic acid, which is nothing but your tartaric acid, which is there in your syllabus, tartaric acid. Now, here I have written the chemical formula. I have written the numbers 1, 2, 3, and 4. So it is 2,3-dihydroxydioic acid. Now, again, we have 2 chiral centers present in these molecules, carbon number 2 and carbon number 3. Now, I have written down there, if there are 2 chiral centers, how many stereoisomers are possible? There can be 4 stereoisomers. So I have written, first I wrote it in this fashion, then I wrote the mirror image, then I drew it in this fashion, and then I drew the corresponding mirror image. Now, as you know, these are non-superimposable, these 2 stereoisomers, that is stereoisomers 1 and 2 of the tartaric acid, they are kind of non-superimposable mirror images, so that means they are optically active. So optically active means they would be able to rotate the plane polarized light. So if that is the case, then that what means that this particular configuration, that is the one in which OH is on the left side, which is the capital L, this is dextrorotatory. Plus sign means dextrorotatory. That means this would be able to rotate the plane polarized light towards the right, which can also be represented by a letter called small d. Similarly, this one in which OH is coming on the right side, this would be represented by a letter called D. And this is levorotatory, which also can be represented by a small l. So this is L plus your tartaric acid, and this one would be your LD minus tartaric acid. Coming to the third and fourth stereoisomers, this we have already discussed in our live session. I'm just revising you. So if you see these mirror images, they are superimposable. Now, why they are superimposable, I've discussed in the previous video. Now, these are if they are superimposable, that means they are optically inactive. So they won't be rotating they won't be having any effect on the plane polarized light because of the presence of the plane of symmetry in these molecules. These are same molecule. So if you are asked at how many number of stereoisomers are possible, you will draw the 4-1 and ultimately you show that only 3 stereoisomers are possible because the fourth one is same as the third one. Okay, they are both the same molecule. So these two are optically inactive. These are optically inactive. Now finally, I would like to introduce one term which is not in your syllabus, but it is important that you should know about it, and that is about racemic mixture. Now, racemic mixture is what? It is an equal amount of if you take equal amount of your levorotatory lactic acid and your dextrorotatory lactic acid, if you take 50% of dextrorotatory, 50% of the levorotatory lactic acid and mix them to, what do you think the optical activity of the mixture? It would be showing no activity because equal amount would be rotating in the left, equal amount would be rotating to the right. So they would cancel out. So the net effect is this mixture, which contain equal amounts of both the plus and the minus, would be optically inactive. So racemic mixture or the racemate is nothing but equal mixture of the dextrorotatory and the levorotatory enantiomer. And this mixture is optically inactive because they contain equal amounts of both the dextrorotatory and the levorotatory isomers, so this would be optically inactive. So these two are enantiomers. So when you mix equal amount of enantiomers, they would form a racemic mixture or a racemate, and they would be optically inactive. Similarly, these two are again enantiomers because they are mirror images of each other. If you mix two equal amounts of the dextrorotatory tartaric acid and a levorotatory tartaric acid, they will form a racemic mixture, and that would be optically inactive. Okay, so just keep in mind what do you mean by racemic mixture. So that is all I want to discuss in this particular video. Thank you for your attention and may God bless you.